Welcome to Veteach. Today's class we will continue with what we have discussed, components and deployments along with their component and deployment diagrams. So what is a component diagram used for? A component diagram has a set of components that can be rendered along with its relationships. So graphically, a component diagram is a collection of vertices and arcs. The vertices are the components and the arcs are the transitions that we were talking about. Transitions or the connections that exist between different components. So what does it contain? It contains components, it contains interfaces and different types of relationships that we were speaking about. Dependency, generalization, association, and you can have realization because of the interfaces we have. What is a component diagram used for? Component diagram is used to model, 1, to model source code, 2 is to model executable releases, 3 is physical databases, and 4 is adaptable systems. We'll take up one by one. It can be used to model source code. So what do we mean by a source code? As we said in components, a component can be used to represent a source code, and so a component diagram can be used to model source code. So what is a source code? It's a collection of different coded files that we have generated by using a programming language, that we will be generating by using a programming language. All that can be generated with the help of reverse or forward engineering that is possible over the different UML models. So as these are collected together, those can be rendered as packages, as executables or files or documents or anything other than that, like tables and other things like that. They can also be related with the help of relations we have, like dependencies or associations or realizations among them. So to show you an example how those modeling of source code can be done, I see here there are a number of header files, .h files, and then there are executables .cpp. So these are interrelated. These are interrelated with the help of relationships among them. So when they are being related, when the source code files are being related together, those can be done with the help of a component diagram. So it is used to model source code. It can also be used to model executable releases. So when releasing a model, when releasing a product, we tend to see that some of the code has to be exclusively available. So what is that represented as? That is represented as a executable release. So some of the abstractions that we tend to do are hidden and some of them are given. So the level of abstraction is what matters when performing this executable release. So to do that, we can use specific stereotypes. We can use specific stereotypes and render them as the components, the executable files. For example, I see here there is a .dll file being shown, which is actually my the interface components that are being related here as executable. So these are collision, driver, and a path, indicating that these are related together to perform a self-test in case of an executable release. And then I have the third is it is used to model physical database. So for example, if I say there is a database being created for a college, so there is a lot of tables that are being created during that time. All those tables, when related with each other, that marks it to be a component diagram here. So that component diagram is our physical database. So the tables that we have related one with the other one now is treated as a component there. So each component, each table when relates with another table, a component is created, another component is created, and there is a relationship between them. If one table is altering another table, data, we tend to see that when an operation is performing on one component, one table, it tends to modify data on the other table also. That can also be shown with the help of a physical database. So to show that, yes, taking up an example for that, you see here that there is a school database being shown. Physically, a stereotyped component has been shown. And there are tables, 1, 2, 3, 4, 5 tables, which are also again stereotyped tables. A table has been created for course, department, instructor, a school and a student. All these are being shown with an association relationship with a bond of aggregation. So what do we mean by a bond of aggregation? We mean that this is the whole and these are the parts. To exclusively show the whole and parts, we have used this diagram, a component diagram, which is actually showing you the logical database schema, which tables are connecting with which one and which place as a whole database. And lastly, to model adaptable systems, we can have adaptable systems. Adaptable are basing on time and location. We call a system to be adaptable basing on time and location. For example, there is a version released for a file. We know that whenever it gets updated, the file name does not change, but the version name changes. So how do we show that in the UML? We show it with the help of adaptable systems with the use of tagged values. So use of tagged values over the components will render them as adaptable. So how do I add a tagged value? Adding a tagged value, the name of the component does not change, but the tagged value will be showing a different value. Like for example, I said there is a version v1 and the same name, the file name does not change, but the file name has a tagged value now, that is version v.2. So indicating that the same file and file, maybe I'll write it as a file 1. So file 1 is version tagged value as v.1 and the same file 1 is tagged as version v.2. So the same file but existing at two different times is what we indicate by this. If it is not time, you can write it as a space also. Like this is not version v.1 but located at maybe a location A, and this is at a location B. This is at a location server A and this is at a location server B. So the location change is indicated by the tagged value. So you can see an example here for modeling the adaptable system. There is a same school database, school.db, but with a server A and a server B. What is the tagged value that we have used? We used a tagged value location. So how did we write the tagged value? We put it in the flower braces, as you can call it as a location, which is a tagged value with a value as a server A or as a server B. Or in another sense, I used an example where I was trying to show you a version assigned as version v1 or version v2 or for that sake anything. But the file name does not change. So those representing such a system is called as adaptable. Coming back to the last form of diagram that we have, it's a deployment diagram, a more reasonable physical representing diagram that can relate to our complete system as a whole, architectural form of representation, which is a deployment diagram. So it shows the configuration of the runtime processing nodes and their locations along with the components. How are they located? Where are they located? All that can be shown with the help of a deployment diagram. So physically, graphically, we represent a deployment as a node, a cube. So all cubes represented and the connections among those nodes is physically called as a deployment diagram. So what does it contain? It contains nodes, it contains relationships, dependencies and associations, and you may have all other types of diagrams also being represented within a deployment diagram along with constraints, tagged values, stereotypes, all that. What is it deployment diagram used for? It can be used to model embedded systems, it can be used to model client server systems, or it can be used to model fully distributed systems. So to model an embedded system, the logical example would be to show you an embedded system, what are the different components that an embedded system has, what is it being designed for. An example shows here that there is a Pentium motherboard which has been embedded with a serial port, with a digital port, right position encoder and a left position encoder, and a ultrasonic sonar sensor. There is a timer, there is a steering motor and a drive motor, all together being put into one Pentium motherboard, which is represented as a node. So how did we call this as? This is a node as a processor combined with so many components together, so which we call it as an embedded system. So you can use deployment diagram to show physically where the components are existing, like all these components are existing over the Pentium motherboard node. It can also be used to model client server system, as in the previous example we said a client server architecture can be specifically shown with the help of a deployment diagram. To show you an example, yes, there are two processors, processor 2, processor 4, with the multiplicity being shown. Physically, that's a server put into a package, and the clients are at a different location. Those are connecting with the servers with a connection. So physically denoting, there is a processor 1 and a processor 2, a caching server, and there is a exclusive server where to speed up the process of data retrieval we have used a caching server. So in any case, the servers are connecting with a simple connection, and the caching server is connecting with the clients. So you see that there is a physical client server architecture being shown here, that these two clients can interact with the server only through the caching server. A deployment diagram can also be used to represent fully distributed system, a fully distributed system. How are the components and nodes physically located at? So we know that our data gets stored at different locations, like there is an Indian server, there is a Dubai server, there is a Russian server, there is an American server, but the data gets stored at different locations. So to show where my components are being stored physically, I tend to use a fully distributed system. So fully distributed system along with the processors and clients and all that can be shown with the help of, globally it can be shown with the help of a deployment diagram. So you see here there is a regional server, and these regional servers are connecting to a country-wide server. So a country-wide server, meaning that this is a physical location. I am trying to denote it as a physically located location, like I am calling it as a Dubai server. So a server physically located at Dubai. So, and there is a logging server. Does it mean that a logging server exists directly at Dubai? No, a client does not know to whom he is interacting. He interacts with through the internet, and the local regional servers are the ones that interacts with the other servers. There is a large form of global representation for such a network. All that can be shown with the help of a deployment diagram. So in a sense, deployment diagram can show you physically how things exist. Thank you.